All right, this is a video on logarithmic functions. We'll do an introduction to what logarithms are, and then we'll do a few different examples where we will evaluate logs. We'll look at a couple graphs of logarithmic functions. But as the introduction, as the motivation of what I want to do here is I want to think about trying to solve this equation right here, 2 to the y equals 12. How could we isolate for y? And you might think, okay, 2 cubed is 8, 2 to the 4th is 16, so y is somewhere between 3 and 4. We could guess and check. We could try 2 to the 3.5. We could try 2 to the 3.6. But we don't yet have a formal, straightforward way of isolating or solving for an exponent. And that's what logarithms allow us to do. So I want to give you a definition of logarithms first, and then we'll go back and look at how they can help us solve for an exponent. So the logarithm of x is defined as follows. If we have an equation of the form b to the y equals x, we could rewrite that in this form, log base b of x equals y. Okay, that's how I'm going to define logarithms here, as simply a rearrangement of an exponential equation. So those two equations that I'll circle right here are absolutely equivalent mathematical statements. They're just written in a different form. Okay, and look at what that gets us. It gets us the exponent isolated for it. It gets the y by itself, the exponent by itself. Now, of course, we then have to figure out what it means to do log base b of x. How do we do that on a calculator, for example? But we have the fundamental step has been done where we've isolated for y already, and that's a huge step here. We have some restrictions here. Let's see here. B has to be bigger than 0, so we're dealing with a base that's larger than 0. We're not dealing with a base of 1. We can't work with a base of 1. And we need to work with an x value that's positive. Okay. A couple things that I like to think of is just to help me remember how we do that rearrangement, what logarithms are, is I try to remind myself that a logarithm is an exponent. Okay. So when we do the logarithm base b of x, it's equal to y, and y was the exponent in that other equation. And I also try to just similarly help myself remember. I try to recall that logs help us isolate for an exponent. So when we have the log of something, that's equal to an exponent. Let's do a couple examples just translating between forms. Okay, so if we have 2 is equal to log base 10 of 100, using the form that we were looking at before, we have a base of 10 and exponent of 2, and it's going to equal 100. So we could write our answer as 10 to the 2 is equal to 100, which we know is correct. 10 squared is 100. But those are equivalent statements. We just did a rearranging. And I like to think of it as sort of this cycle or circle that I'm going. 10 squared is equal to 100. Okay. Next one, log base 4 of x is equal to negative 3. Similarly, the base raised to what the logarithm is equal to is then equal to what we're taking the log of. So we can write this as 4 to the negative 3 is equal to x, and we could solve for x if we wanted to figure out what 4 to the negative 3 is. Similarly, down here, log base 5 of 125, log base 5 of 125, so we're going to do 5 to the x is equal to 125. You just want to get really comfortable with doing that translation from log form into exponential form, and here we'll go from exponential form into log form. So over here we have 3 to the x equals 100. I like to remember that logs isolate for the exponent. That's the whole point of logarithms, or one of the points of logarithms. Our base is 3, and we're taking the log of 100. X squared is 9. Logs isolate for the exponent. Our base is 2. Excuse me, that's not correct. Our base is x, and we're taking the log of 9 base x. And lastly, 1/2 equals log base 16 of x. Okay, so we're just following rearranging a pattern going between logs and exponents. Evaluating logs, we're going to actually try to do this without our calculator at this point, just try to do these by hand. So for this first one, we have log base 8 of 32 equals x. We could rewrite that in exponential form and think about what's x if 8 to the x is 32. It's still not exactly clear, but both 8 and 32 are powers of 2. So we can rewrite this as 2 cubed to the x equals 2 to the 5th. And then follow our exponential properties where we have 2 to the 3x equals 2 to the 5th. And once we have equivalent bases, common bases, we can say that 3x is equal to 5, so x is equal to 5/3. Okay, so we can say over here then that log base 8 of 32 is equal to 5/3. For this next one here, log base 5 of 125. Again, we don't have a clear intuitive understanding of what the logarithm is at this point, but we can transform it into exponential form. And we could write this as 5 to the x is 125. So 5 to what power is 125? Hopefully you can do that in your head and realize that it's 5 cubed, so x will be 3. And lastly, we can do this third one, 64 to the x is 1/32. So we'll rewrite it in exponential form, which, as I've been saying, is a little more familiar. All right, and then we can get a common base as well. 64 is 2 to the 6th. So 2 to the 6th then raised to the x. And 1/32 is 2 to the -5th. Okay, so here we can apply our property of exponents, where we can say 2 to the 6x is 2 to the -5. And then once we have a common base, 6x equals -5. So x will be -5/6. That would be our solution there. All right, so that's just rewriting into exponential form and then getting a common base. I want to do a little bit with graphing here. I want to graph first y equals 2 to the x. That should be a common, straightforward graphing task for you. And then I'm going to secondly graph y equals log base 2 of x. So let's graph y equals 2 to the x, and let's graph this one in red. We'll try to color coordinate here a little bit. Y equals 2 to the x. We're going to get a graph that looks something like this. Y-intercept of 1. It's a doubling pattern as we go to the right, and our y values are getting chopped in half as we go to the left. If we wanted to graph y equals log base 2 of x, that would be equivalent to graphing 2 to the y equals x, just doing that same transformation between logs, or translation between log form and exponential form. 2 to the y equals x, which I have circled in purple there, is just the inverse of 2 to the x equals y. So my red and purple graphs, those functions, will just have x and y coordinates swapped. That's what it means for something to be an inverse. So let's go ahead and plot those. So for example, this point gets mirrored over there. This point gets mirrored over here. Oops. Gets mirrored over here, etc. Okay, so our x and our y terms are swapped. And we can graph something that looks like this. Has a y-axis as an asymptote. Let's clean this up a little bit. And you should be able to see that it's a mirror image. It's symmetrical. My red and purple graphs are symmetrical across this y equals x diagonal line. Okay, so that's what it means for two functions to be inverses of each other. They're symmetrical across that line. So that purple function there, y equals log base 2 of x, is probably the most fundamental log function that you'll need to graph. We'll do one more, and I just want to show you some rules, some transformation rules for these log graphs, and these are nothing new. We've been looking at these in different functions all along. If we have an a value multiplied out front, it's going to be either a vertical flip across the x-axis or a vertical stretch or compression. So that would be a right there. If we're dealing with h is going to be a horizontal shift. And keeping in mind that if h is greater than 0, we're shifting right. If h is less than 0, we're shifting left. But also keeping in mind that standard form has a subtracting h inside those parentheses. And lastly, if we're adding on k at the end, k is the most intuitive transformation, I believe. It deals with a vertical shift. If k is positive, we're shifting up. K is negative, we're shifting down. Okay, so let's practice this real quick with one transformed function, and then we'll be done. So what I actually want to do first is simply graph y equals log base 4 of x, and then I'll apply the transformations. I'm going to plot this one in red. Y equals log base 4 of x. So we will have, so just keep in mind that is the same as 4 to the y equals x, right? So it's the inverse of 4 to the x equals y. So what that means is we have a y-intercept of 1, 0. As y gets larger than 1, it gets larger by 1, x will increase 4 times. So we have a 4 right there. And then our next one will be out 16. Okay, so it's a very shallow increase, and I'll try to sketch in this curve. And it again will have a vertical asymptote of the y-axis. So it's going to look like the inverse of the y equals 4 to the x function. So then what we can do is plot the transformed function. Let's plot this one in purple. And I hope you can see that each point on my parent function will be shifted right 3 and up 4. And we can just take each of the 3 points that we have and apply that transformation and sketch a new curve. So for this point right here, I'm going to shift it right 3 and up 4. I hope you can see that our asymptote, our vertical asymptote, is just going to be shifted right 3. So I will get a new vertical asymptote in here. And then my other points will be shifted right 3 and up 4 as well. So this point, 1, 2, 3, 1, 2, 3, 4. And lastly, this point, 1, 2, 3, 1, 2, 3, 4. And I can sketch in a smooth curve from there. Sometimes it's hard to make a nice smooth curve when we're dealing with such a sort of an extreme sequence here. But that would be our new graph, log base 4, the quantity x minus 3 plus 4. So a transformed function shifted right 3 and up 4. And that is a great place to stop right there.